Can you hear me okay? Yeah.
All right. So our next talk is on EREQ, regular expressions with quantifiers and incremental quantifier elimination by Ekaterina, Zhuchko, Ian, Varatalu, Margus, Veanes, and Nikolaj, Bjørner. And Ekaterina will be giving the talk.
Thank you. So you introduced us all already. Let me start with the motivating example for this work, which is learning specifications from traces of a cloud storage service. A trace in this context is a word over an alphabet of actions. In a simplified setting, these can be things like updating an object or deleting or undeleting it. The things that we want to learn can come in different shapes as well. For example, enabling conditions. Something of the form delete enables undelete. So undelete can only occur after delete has already occurred. Now, this condition is naturally expressed as a first-order logic formula. For all positions in the trace, if undelete has occurred, it means that previously, at some point in the trace, delete has occurred. Similarly, we would like to express disabling conditions. So for example, delete disables next delete, which means delete cannot occur twice in a row. Now, this thing is more naturally expressed as a regular expression of this form, where the body says match anything, then we have a sequence of 2 deletes, and then anything again. And this pattern should not occur. So the key observation here is that different types of conditions require a different notation of formalism. So the question is, can we have one language which supports both of them? The answer is, of course, yes, and this is what this talk is about. EREQ allows us to switch between the two, or more like it has both of these formalisms, so you can use quantifiers when necessary or regexes when it's more natural. One thing is that regular expressions cannot express position-dependent properties. So where do you get the quantifiers from? We start with weak monadic second-order logic, which does have quantifiers. And the variables range over positions in a word or finite sets of positions. Now, the atomic formulas come of several shapes. So we have predicates, which assert that at a certain position, a label holds. We have order and subset relations, and we also have a singleton construct, which allows us to essentially eliminate talking about first-order variables. Now, there is a celebrated result, which says that wMSO has the same expressivity as regular languages. Now, the small caveat is that the corresponding decision procedure has non-elementary complexity. Nonetheless, almost 30 years ago, some researchers in Aarhus developed a wMSO solver, which was actually practical. There's some really clever engineering. So despite this horrible worst case, they were able to solve practical problems. And it's still the state of the art today. Let's now look at the decision procedure, so the classical approach, which is also taken by Mona. We start with a wMSO formula. We translate it to a finite state automaton. And then we check emptiness, which corresponds precisely to check and satisfiability of the formula. Now, to explain the cost of this construction, let's consider the formula not exists x, such as phi. This approach builds the automaton from the innermost formula. So we start with the automaton for phi. Then we have to deal with the quantifier, which introduces non-determinism because it corresponds to projection. And then we have a complement, so we are forced to determinize. And this is where the exponential cost comes from. Now, if you imagine a more complicated formula with several quantifier alternations, each one of them essentially adds an additional exponential cost. And this is where the non-elementary complexity comes from. We have a tower of exponentials, which is stemming from these quantifier alternations in the formula. And now the question is, can we avoid constructing the automaton explicitly? In our work, we instead translate the wMSO formulas into EREQ. And then our decision procedure is based on symbolic derivatives. So we lazily explore the state space and then check if some state is nullable, meaning the empty word is in the language of that state. And what does it give us? Well, it's a lazy top-down exploration using symbolic derivatives as opposed to the bottom-up approach taken in the classical decision procedure. And then this way, we avoid explicit automata construction, which is what we wanted to do. So let me introduce EREQ and the corresponding decision procedure. So really, EREQ is a conservative extension of ERE. So the new operator is the existential quantifier. One thing worth mentioning is that is non-standard. Instead of concrete characters, we are working modulo an alphabet theory, so we have a set of predicates. And these predicates come of two different shapes. One of them is the lowercase alpha. You can intuitively think as character predicates. So you can think about, I don't know, digit, or lowercase, uppercase letters. Whereas the PIs are an artifact of introducing the quantifiers, and I will explain a bit more on the next slide. The universal quantifier is just syntactic sugar defined in the usual way. And then the interesting part is that the semantics of the existential quantifier require us to extend the alphabet. So let me explain what I mean by that. So we take our alphabet sigma and we extend it with bit vectors of size n, where n corresponds to the number of free variables in the corresponding formula. Let's look at a concrete example. So we have a word BBAB, and then we have two variable assignments. So there's two free variables in the formula. And now the extended word is of the following shape. So we have this table where the first row is just the character component in the usual way. Oh, sorry, I had highlighters, but they do not show up. So I'm going to try to use this. So the first assignment tells us that the positions that are active are positions 2 and 3. So the first row marks precisely those positions. The rest of them are false. Similarly, the second assignment tells us that there is 3 active positions, 0, 1, and 4. So the last row marks precisely those positions, and the rest of them are false. So in that way, we're able to map the variable assignments into the words. And now the role of the two different types of predicates are clear because we have the character component and then we have the propositional component, which is a way to encode the assignments. So with this, we can define the semantics of the existential quantifier. We are using projection here, but the idea is that we project away one of the quantified bits. So essentially, we just remove the row of all the words in the language, going from n+1 variables to n. So for the translation, the Boolean operators and the existential are quite straightforward. They just map to the corresponding counterparts in EREQ. The more interesting part is the atomic formulas. So let's look at the first constructor. So the wMSO formula is telling us that so xi is just a second order variable, and there is some position that has the label alpha. And now, in order to translate it to a regex, we are taking advantage of the two types of predicates. What we're saying is that the regex is matching anything, and then at some point, we would like to state that both the alpha component and the propositional component are true at a certain position in the word. And then again, we don't care what happens after. So similarly, in the other cases, we are just using the predicates in order to encode the constraints from wMSO formulas into the regexes. And then we formally prove that the translation is correct. So if a word is in the language of the formula, then the encoded word is also in the language of the translated formula. I mentioned that the key ingredient of our decision procedure is symbolic derivatives. So you may have heard of Berzovsky derivative, which is an old concept. So the derivative of a regex with respect to a single character is just all the continuations after reading this character C. In our context, a symbolic derivative of a regex is a term tree. So instead of encoding it character by character, we encode all one-step transitions in a single symbolic step. So here I have an example for the base predicate. The symbolic derivative of some alpha is a tree where the node contains the predicate, and we have two leaves. One is epsilon, one is bottom. And the idea is that you can later evaluate this tree with a concrete character, and depending whether the character matches the condition, you either go left or right, and you end up in two different states. We show that this definition respects the semantics. And here, the idea is that if you take the symbolic derivative of a regex and then evaluate it on a concrete character, what you get is essentially the classical definition. Except now we can replace many concrete steps with one symbolic one. And this symbolic structure is exactly what enables us to introduce a new rule for the quantifier. The idea with derivatives is that we want to have nice algebraic rules, and since we extended with the existential quantifier, we want to keep that. So what we managed to achieve with this is that derivatives also distribute over the quantifiers. Of course, with the universal quantifier, it's just a consequence of the fact that complement and the existential individually distribute. So it's a combination of those. But what this means is that we can eliminate the quantifiers incrementally during construction with the derivative. So remember before, with the classical procedure, we were forced to determinize. But here, we can have the incrementality that we wanted. And the idea is that we don't need to construct the full automaton upfront. Another thing is we have some nice algebraic laws. So the existential distributes over concatenation, the Kleene star, and disjunction. And the reason why it's interesting is because we can eagerly do rewrites during construction and, again, simplify the expressions, trying to prune the state space as much as possible. So now we have all the ingredients for the decision procedure. We start with the wMSO formula. We use the translation that I showed earlier. And then we unfold the symbolic derivatives, exploring all the reachable states, and check in nullability. So if we reach such a state, then we get the satisfiability of the original formula. Now, one important question here is, does this procedure terminate? And what this really depends on is whether the derivative closure is finite. And indeed it is. We, again, formally prove this result. So now all the theory is in place. Let's look at some evaluation of how this performs in practice. We have implemented the solver in Rust. And first, I will demonstrate the evaluation on random benchmarks. So compared to Mona, as I say, this state of the art. It's no surprise that Mona still leads overall. I mean, we're competing with 30 years of optimizations. But EREQ is still competitive on the 10,000 benchmarks that we tested on. And one interesting thing, as you can see, there is two blue curves for EREQ. The lower one is essentially choosing the best configurations amongst all for each benchmark. What I mean by that is we are switching between different normal forms and then choosing the best out of the ones available. This is a new axis of optimization because Mona, in some sense, commits to one normal form at the beginning, whereas we are able to exploit several normal forms, for example, negation normal form, CNF, DNF, or anti-prenex normal form, and then utilize the best one. But really, the more interesting set of benchmarks is the structured benchmarks. So we have several families, including counter, which encodes binary addition problems, and lift problems, which is essentially a specification of an elevator system with the parameter n corresponding to the number of floors in this system. So EREQ solves all 50 problems, whereas MONA solves 30 out of them. And the ones that MONA cannot solve are precisely these counter and lift problems beyond a certain bound. So the two solvers have different failure modes. For MONA, it essentially hits a space wall, whether it's the limit on the BDD nodes or out of memory. For EREQ, we hit the time wall with the 60-second timeout. Now, one of the things we haven't utilized yet is understanding which of the normal forms is best. At the moment, it's kind of a future work to experiment and really take advantage of this, axis of optimization. So we believe that there is a lot of more work that can be done in order to bring us closer to MONA on the, for example, random set of benchmarks. Okay, so in summary, we introduce extended regular expressions with quantifiers, which have the same expressiveness as wMSO, with a linear time translation. The key insight that we have is that the derivative distributes over quantifiers, and we can incrementally eliminate the quantifiers during construction. All the core theory has been verified in Lean, and we have a prototype solver in Rust, which has competitive performance with MONA, especially on the structured families of benchmarks. And as for future work, we would like to revisit many of the applications that MONA introduced, including things like protocol verification. And also, one thing that's missing from the current benchmarks is the regex fragment of EREQ is not really tested. I mean, concatenation, star, and the modular theory aspect. And as I mentioned, we would like to investigate the different search strategies and how to utilize them in the future. Thank you, and I'll take any questions.
All right, we have time for a question or two.
Hi, great talk, Tom Ball, University of Washington. So what data structures are you using? Are you using BDDs or anything?
Yeah, we're also, yeah, exactly. We're also using BDDs to represent, well, both the predicates and the transition term themselves are sort of like multi-terminal BDDs. So we have like two layers of BDDs, you could say, for the predicates and for the transition terms.
So the fact that you're not getting the space outs, but is the fact that you're doing things lazily. You're not using, like MONA is using them much more aggressively because they're representing the eagerly constructed automata, and there's just many more nodes in the BDD?
Yeah, exactly. Okay. And yeah.
Hi, Cass Alexandru, RPTU Kaiserslautern. I wanted to ask, so essentially this derivative sort of, you can think of it as walking through like an automaton that isn't fully constructed, right? In some sense.
Yes. Oh, let me be also upfront here. So in the cases where the problems are unsatisfiable, I mean, we cannot avoid the worst case, right? We may be still exploring the entirety of the state space. What we can do is aggressively prune it on the fly through like rewrite rules, for example. Yeah.
What I wanted to ask was, So I don't know about how Mona is implemented, but would it theoretically be possible to have like a solver that constructs like the determinized automaton, but in a way that it does it lazily, and then that sort of the evaluation of like a path of a trace in that automaton would correspond to this symbolic derivative, or is that not possible? Because you said there's this bottom-up thing going on. So is it like, do you have to build the entire automaton?
In the case of Mona, yes. I know some people have explored other methods, but I'm most familiar with Mona, where they just have to explicitly construct the automaton and determinize, they minimize the automaton quite frequently. So that, yeah, you cannot escape this in their setup, but I'm not sure if in general, maybe you can do some clever tricks to avoid it. Yeah.
Because I'd just be curious if it would be like technically possible if you don't construct like the sort of the data structure completely upfront, whether sort of a path through that data structure and a lazy construction of the data structure would be the same or like equivalent to this derivative. But anyway.
Yeah, please.
How does this work? Okay. So I would like to comment on this. The core issue is classical techniques do not allow you to propagate complement. So you have a fixed finite alphabet, you have to construct the automaton explicitly, then do the power set construction explicitly, and then you can determinize. The fact that you're using derivatives with symbolic predicates allows you to propagate complement over the two branches. You cannot do that with a classical finite alphabet. It just makes no sense. You have to have an if then else case where you can just apply this rule. So that's the difference. Yeah.
All right, let's thank the speaker again.